So your beta appear to be spin up because the energies are higher than the alpha.
So both of these are spin down.
No, the beta is up. So I don't know which one.
This one's alpha and this one's beta.
Right, because if we look here. Oh wait. No, these are the higher. So these have extra. Oh, lower energy. Yeah, sorry. This is these are higher than this, right?
Yes.
Because this is we're on negative energy. So these alpha spin up, sorry. So then if we look here, this is negative half and negative half. And those that spin up. So both are spin up. And then you can kind of see that they aren't really paired well. Right? Because this is like negative 6, this is like negative 8. So it's the states aren't totally efficient. But yeah. Why do you ask?
Well, I'm supposed to talk about this here in about 10 minutes. So.
Oh, but I understand that you're going to talk about it, but why do you ask?
I didn't understand when Dimitri talked yesterday what the alpha and betas all meant. That's all.
Oh,
So you must have read this unrestricted then, since they're.
Yes.
Yeah. Okay. Yeah.
But is that a real determination then?
Yeah.
Yeah, it should be.
Orbital scheme drawn.
They should be.
It should be.
Yeah.
But
Not necessarily are.
yeah.
They're close.
Whoa.
Beta's homo and alpha's homo -2 are about 0.15 reduction volts
My
off.
presentation is so big, I
Which
think I won't be able to complete it
is
within the
about-
time. Yeah.
Okay.
So
20 0.2 electron volts different? So, no, it's like 2 electron
26 or
volts.
something like that.
27 point something.
Okay.
So what?
so my alpha has more orbitals than the beta.
Yeah, so that just indicates that you have
More spin up,
more spin up.
which makes sense.
Oh. Okay. Now I understand. So all the spin ups are in alpha, and all the spin downs are in beta.
That's what I was trying
So
to tell you.
This-
This is what I was trying to tell you. The thing that I've been saying is that, you know, your MO schemes suggest they should be paired, right? So they should
They
be degenerate.
Well, but
they're not too.
the homos are.
No. They're close. They're
The
like
two spin ups.
really close.
Negative 0.55.
yeah, but if you look at alpha beta, the states these states here are not degenerate.
Right, that's what I'm saying, is whether they should be spin paired.
The time here in the room is not quite correct.
Yes.
So the
Yeah.
I don't know what we mean in random description.
maybe able to do like 3, not longer than 7 minutes.
Genesis goes.
I don't know. I didn't.
Yeah, I think I can do
Did you
it.
try it?
You had
Yeah, it's
Otherwise, they
six,
would have to be degenerate.
Otherwise, it would be
6.5
just
minutes or
alpha.
7 minutes.
Why just
Maybe I have to remove one.
Because I converted it, to run Gaussian. So it didn't actually. Like it just didn't go yesterday.
I believe if you have beta electrons, you have to run unrestricted.
Okay.
But if you have like alpha occupied, alpha virtual, beta occupied, beta virtual, if you have the beta,
Yep.
it's
Yep.
Good afternoon. Thank you for coming to this session. This is an important part of the computational chemistry course 476 and / something. Today we have a special meeting by when the attendees of the course will share their experience with each other. The main goal of the meeting is to fit in time. This is a top priority because it is so hard. We set up a goal to spend 3 minutes per presentation, but you will see that it is not possible, that it will be longer and longer, and I will try, I do not know how to be hard and demanding, but I will try my best to cut according to the schedule. The handouts at your tables contain printouts of what everyone completed, so that you can listen to your classmate, follow, ask aggressive, nasty questions in order to learn more. But within no longer than 7 minutes for presentation and questions per person. Otherwise, we will be kicked out of the room without giving chance to speak to the whoever at the end of the schedule. What are we doing? So we are in this introduction, computational, quantum chemistry class. The presentations are loaded there into the computer. I don't know if it is possible to jump and switch slides without going from the focus of the computer, but we can do a quick jump. So an overview of what the course does. The goal is to get practical skills for computational characterization of materials. One put in theories, one put in atomic models, and then by using right software and the right hardware, one can compute observables and compare them to experiments. Last time, the course is composed of 4 parts. Last time, at the end of each part, we have student presentations. Last time, we learned practical and shared experience how to build models, how to rotate, change their bond length so that you can use it in your research. Now we are computing the basic level of computing electronic properties, electronic structure, basic observables of any model with so-called Gaussian software. And there will be a couple of presentations more. So, once again, 3 minutes per academic presentation, 1 minute to walk to the stage, 3 minutes for questions, 1 minute to go back. It is a very hard task, much harder than to prepare and to present. So try to self-control. Typically, one uses 2 minutes per 1 slide. Most of you have 10 slides. You need to speak very quick. And skim through slides like crazy. So once again, here is the list. The slides are enumerated. The files with slides are enumerated 1, 2, 3, 4 in the order they should be presented. And just in case, the files are named according to the first name of the presenter. So, as you can see on the screen, here is the first, second, third. So you just click on it, it pops up, and you start presenting. Questions on the protocol? Good. So, with this, I would like to announce presenter number 1, Brandon Disroot, who will increase our knowledge in the aspect of what are computational methods and how they are implemented in Gaussian software. Floor is yours. I'm starting to count time.
All right, I'll try and go quick here. My name is Brendan Disroot, and I'm going to give a brief overview of electronic structure methods in computational chemistry. First off, what do these do? The most simplest way to say what they do is they help us calculate the energy of a system and the parts of the system, the energy in those. And those will...
Try to come closer to the screen. Yeah, this one, yes.
All right. And those will help us get some useful outputs, like we can find the geometry, and the absorbance and band gaps of semiconductors and such. As you know from using the Gaussian software, there's a plethora of computational methods, and if you've ever wondered, the abbreviation's got the full name on this side. But I'm going to be focusing on kind of the top of that list there. And let's jump into it. The molecular mechanics method really it's important if you run this that you specify the bonds between the atoms, because it will treat the bonds as if there's like two masses with a spring in between. And you can really see that in the energy equation there. It's like, your 100 level physics spring equations for a lot of those terms. And, atoms that aren't bonded together, like two different molecules, it'll just run calculations with like Coulomb forces and van der Waals. That's, the easiest to compute. But moving on to what we've been learning a lot in class is the Hartree-Fock methods. The regular Hartree-Fock methods will simplify the many-body Schrodinger equation by a couple ways. Firstly is by having electrons get acted on by a mean field instead of, potentially hundreds of other electrons, making it, a one interaction instead of hundreds of interactions to compute. And then you can estimate the many-bodied wave function for all of the different parts as just a single Slater determinant. Based off the Hartree-Fock method, there's a couple others, like the semi-empirical method, which is like Hartree-Fock, but it excludes some of the computation parts and will just substitute in experimental data for those. And then the Muller-Placet, which will run a regular Hartree-Fock calculation and then add in a polynomial at the end with, like when you're choosing the method, there won't be an n, there will be a number, and that's how many terms in the polynomial there will be. Finally, there's going to be EFT, which I'm going to mostly skip over here because we'll be learning about that in the next section of our class. So if you're a guest, feel free to stop by next presentation to get all you want and more. So, in conclusion, there's basically the best in computational cost are going to rank worst in precision. And you really just want to find a balance for how precise you need your results and how long you want them to be running. If there's something that was just more precise for less effort, everyone would use it and there'd be no other methods. So, yeah, that's about it.
Okay, please join me in thanking Professor Brendan. And
questions?
Whitney, please.
So the cost, which one is higher, as in 1 or 5?
1 is supposed to mean better, so it costs less. Where in precision, 1 is more precise. So. Yes.
More questions to Brendan? I do have one. So you show the table like 1, 3, 4, 5. It is like ranking in the Olympics.
Yes.
But which time intervals and which percentage or which absolute values of errors you are talking about based on your personal experience? Is it like seconds, days, years, and is it like fifth digit after the period, or it is like 200% error? What does it mean? Constant precision.
I guess from just relying off some memory, the cost is going to be different on a pretty large scale. Like your easiest, your molecular mechanics runs might be minutes or hours, and the same, more expensive calculations could take a day or more. And then I assume the precision is going to be pretty much the opposite of that. I don't know how you can quantify precision as easily. without like actually testing it and graphing it and whatnot.
Okay, let's thank Brandon for presentation and discussion. And the next presentation is by CHEM476, who will share his vision on the question of selection of basis sets. So please come to the podium. So as you have experienced, it is an important step that no one can avoid while doing calculations, and Faisal would like to share his vision. Floor is yours.
Hi everyone, good afternoon. This is Faisal. Today I'm going to talk about on basis sets. So what is a basis set? Generally, a basis set is a set of vectors which defines a space in which a problem is solved. But in quantum chemistry, a basis set is a set of functions which describes the shape of atomic orbitals in an atom. And molecular orbitals are created by taking the linear combination of these atomic orbitals. So from where does this basis set come from? Actually, Hartree-Fock calculation is the most common type of ab initio calculation. The best part of Hartree-Fock is that in it the many electron Schrodinger equation is broken into many one electron Schrodinger equation, and the solution of each one electron Schrodinger equation yields to this basis function, and the accuracy of the calculation depends upon the flexibility of this basis function. The basis functions are usually described by the two types of orbitals. One is Gaussian type orbital and the other is the Slater type of orbital. If you look at the Gaussian type orbitals equation, you look at the e to the power minus zeta r square. Here zeta indicates the width of the orbital and r indicates the distance of electron from the nucleus. And if you look at the Slater type orbital, you look only here is the e to the power minus zeta r, only a r, and this r square dependence is attributed for the less precision of the Gaussian type orbitals, because for that reason it cannot correctly tell the probability of finding an electron near the nucleus. So we can optimize both those features in contracted Gaussian type orbital, in which a linear combination of Gaussian type orbitals is taken to mimic a Slater type of orbital. And if you look that, this is the equation of the contracted Gaussian type orbital, and here we use the contraction coefficient and to mimic the behavior of Slater type orbital. So according to the size of the basis set, it can be classified as the minimal basis set, double zeta basis set, triple zeta basis set. A minimal basis set is constructed by taking a basis function of each type for one type of orbital, and it is the smallest type of basis set. STO, GTO, CGTO are the common examples of the minimal basis set. STO3G is the most common type of minimal basis set. The notation indicates that this basis set approximates the shape of a STO orbital by a single contraction of 6 GTOs. Here are the double zeta basis set and triple zeta basis set. A double zeta basis set is constructed by taking in two basis function for each type of orbital, and the triple zeta basis set is constructed by taking 3 basis function for each type of orbital. So why do we need to use this double zeta or triple zeta basis set instead of the minimal basis set? Because the electron density in a separated electron density of an atom in a separated condition and electron density of atom in a molecule is not the same due to the interactions of other atoms, and so that in a molecule the electron density of an atom can be predicted by the orbital exponent. So if we use more basis function for that, we can allow the variations for these basis functions. So these double zeta or triple zeta basis sets will be discussed in the later type of basis sets. The split valence basis set. We know in chemical environment the valence electrons interact actively, but the core electrons don't. So the core electrons can be treated with the minimal basis set, and the valence electrons can be treated with the double zeta or triple zeta basis set. This is known as the split valence basis set. Popol basis sets are the most common type of split valence basis set, and 631G is the most popular Popol basis set. The notation indicates that each core orbital is described by single contraction of 6 GTOs, and each valence orbital is described by 2 contraction. One is with 3 GTOs and other with 1 GTOs. The polarization basis sets. A polarization function is any higher angular momentum added to the orbit, added to the basis set that is not generally occupied in the separated atom. It is generally used to represent the electron density in the bonded regions. It is generally denoted by adding asterisks with the Popol basis sets. One asterisk indicates that the depolarization functions are added to the non-hydrogen atoms, and 2 asterisks indicate the p-polarization function are also added to the hydrogen atoms. The diffuse basis sets are used to represent the very broad electron distribution. They are important in representing the anions and intermolecular complex. They are generally notated by the plus signs. One plus sign indicates that the diffuse functions are added to only to the non-hydrogen atoms, and 2 plus signs indicates that they are added both to non-hydrogen and hydrogen atoms. Dunning's correlation consistent basis sets. Thom-Dunning proposed correlation consistent basis sets as basis sets optimized at a Hartree-Fock level may not be ideal for the correlated computation. Dunning's correlation consistent is generally denoted by CC/PV/XZ. CC denotes the correlation consistent, P means polarization functions are added on all atoms, and VDZ, that means valence double zeta, which means the valence orbitals are described by 2 contractions. And if a prefix OG is miskept here, then the OG indicates that the diffuse functions are also added to it. And here is the where the Gaussian, in Gaussian we can use the basis set from this window.
Okay, thank for a very interesting and very dense presentation. So, although we are in the limits of time, we have chance for brief questions. Please.
What do you mean by increasing the flexibility of the basis set?
The larger the basis set, so if we use the 2 basis function increase or instead of 1, that I use the flexibility of the basis set. If you consider more functions instead of 1, there's the flexibility that you can. Okay, in case of split valence, you consider the core orbitals and the valence orbitals separately. There's the flexibility of this basis set.
Okay. If there are no more questions, let's thank Hassan once again. And the next presentation is by Samuel Brown, who will cover the practical aspect that one may need for actual computation of observables for comparison with experiment, related like which observables, which types of calculations can be requested from this Gaussian software. From now on, after first 2 questions, the remaining 8 will be more practically oriented and a little more easy to digest. So for the speakers and presenters, please try to stand near this area if you want to enjoy yourself on the recording.
All right.
Floor is yours.
Thanks, Dimitri. Yeah, my name's Sam Brown, and I'll be going over kind of practical aspects of doing some jobs in Gaussian. So my presentation, will kind of go over what the past 2 presentations talked about with methods and then basis sets. But to perform any calculation, there's 3 main components that need to be done. So you have the job type, the method, and the basis. So looking into the Gaussian software, we've seen this all before. There's a job type where you have energy, the drop-down menu with various different job types. Then there's also the method that can be done, which was talked about in the last presentation. And then there's also the basis that was talked about, I guess, in the last presentation. The method was talked about 2 ago. So job types, I went onto the Gaussian website and pulled up all the different job types that they have: single point optimization, frequency. So these are some of the different job types that you can do when you pull down the optimization, or just the job types. We've all seen this energy optimization, frequency. These all have different things that they'll do, and there's more than just this. So if you wanted to use a different type of job type that's not listed on there, to do this, you would click into the blank at the bottom, like this, and then you'll type in at the additional keywords somewhere the job type that you actually want to do. And then I'll go on to methods. So this was covered in more detail 2 presentations ago, but you also have these different methods: Zindo, CIS, SA, CECL. These all will do different things, which was talked about. So we can use these different methods to predict different molecular properties. So here's a list that's probably fairly hard to see, but say you wanted to look at the thermochemical analysis, you can do like a frequency type of analysis. Or if you wanted to look at the electronic transition band shape, you could do a freak equals FC. And this is kind of how you do different stuff like that. With a little bit of help, we're going to look at the UV Vis spectra of a sample. So I have here 1,3-butadiene absorption spectra. So we've all worked with this molecule, and you can see there's an absorption that goes in at around a peak around 210 nanometers, which is what was calculated. And comparing that to an absorption speed that I just found online, you can see it is pretty similar. So there's plenty of different things that you can do within this software, and that was just a brief overview of it. So,
okay,
points? Any questions?
For being in time, and we have a couple of minutes for asking questions.
How many transitions did you do for the 1,3 butyl?
So I said I had help. I had a lot of help with Dimitri helping me. So 5. I think I did about 5.
5. More questions? I have one. So your vision, we didn't cover it in the class, but your vision, what is the difference between ground state total energy calculations that we covered in the lab and in the class, and the spectral calculations that you presented right now?
They're higher energy. You're looking at the energy of excitation?
Yes, exactly. No more questions? Let's think.
Just a quick question. On the methods, one of them is TDSCF. I'm just curious what that is. What is it? Is it like a time-dependent self-consistent?
Questions are directed to the...
Okay, TDSCF stands for... Oh, I had it written down somewhere, and it's not
slide
that.
6.
No.
If not, in the interest of time, I can ask you later too.
Yeah, I'll have to look it up. I thought I had it. I don't.
Oh, that's fine.
Time-dependent something.
Self-consistent.
Yeah, that's what I think. So.
But in general, his answer was correct. That time-dependent self-consistent field is abbreviation for considering excited states. Another round of applause. And our next presenter is Javed Muhammad, and his third name is Abu. Correct me if it's wrong. So he will provide additional insight how to do the. Please start your presentation. How to request specific calculation from Gaussian software in case you do not have graphical connection to your supercomputer, or you want to go for some exotic calculations that are not included in this mouse-operated graphic user interface. So it will be more systematic and rigorous lesson how to give orders to the computation program, how to request specific calculations. Floor is yours.
Thank you, Dimitri. I'm Mohammed. So actually, last couple of presentation, we know how to do some quantum chemical calculation by using Gaussian software, but we have to give some instruction to the Gaussian software. So for that purpose, we need to make a input file, and we use a graphical software, the Gauss view software, to make that input file. So, and last presentation you also saw that by using some graphical command, we give them some, and then it will create a file. That's actually nothing else, just a SCI text file. So I'm just trying to show you what is this file and how can we modify it with that file without Gauss View software, because last time you saw that there in Gauss View there are some default functions and methodology only, but if you want to use a different function we need to modify that file by ourselves. So this is the one of the typical .com file, and I'm giving an example that I used in our NDSU CCast, not in the USD cluster. That's why they have some extra line here. So they have a 4 section here typically. First section, these are called as a link O commands. It's included some hardware requirements and other requirements and program requirements. We put that in this section. And the next section is just a very important line. This line included all conditions, methods, and other requirements for the run. And next section is just identification, just a name. We want to give a name of our job. By that name, we will not get our job in the later on. And the next section, following section, this is a molecular specification. And in this one, this is an example of a small silver cluster. And the next section sometimes is important, but it's named as optional additional section. Sometimes we don't know that we don't need this section too. So following, just I'm showing elaborately in all sections. In the first section, this section started with the % sign. This % sign means this is the first section. It includes and the MEM. This means how much memory you want, and give them command. This software will ask them for 40 GB RAM memory. And next one is the number of processor, because some clusters they have a default processor, but in our system we can use the different number of processor. Usually Thunder they have a 20 processor in each node, so it's included the 20 here. And Linda, if you want different nodes for a single job, sometimes we need to parallelize this with the node. So this Linda software can parallelize these different nodes, and we can use a more hardware facilities. And last one is just checkpoint file name. Next section, So next section is the command line. Route section. It started with the hash, and hash button means it will take the command from that line. Suppose if I give you example, this line is included different is the optimization OPT, is an CHEM476 relief, is just given name of the functionals, and is a basis set as you saw that in the basis set presentation. Sometimes we have to use the different basis set, more than one basis set. In that case, if we use a gen command here, that will take a mixed basis set, and we need to define that basis set in the last section, optional section. And they have other comment too. This is the solvent section, what solvent and what's the solvent methods, and how is the core potential, we will read those type of commands. And after that, by blank line, we will be terminate that line. You can use the multiple line, but if blank line means the terminate that section. And we will go to the next section. That's just name of this one. And the same way, just blank line terminate that section. We will go to the next section. First one, in the molecular specification section, first line is the charge and multiplicity of the system. First number indicate the charge of the system. It's maybe 0, -1, +1, or +2, whatever you charge of the system. Space, second number. Second number indicate the multiplicity of that system. It's maybe singlet, triplet, or doublet. 1 for singlet, 2 for doublet, and triplet is 3. In the following line, without no space, and the following line, immediate next line, we will give the Cartesian coordinates of our molecular system. If we want to use the molecular geometry from the checkpoint file, we don't need to put these Cartesian coordinates. We can just keep that line blank, and a blank line will make the terminate this section, and we need to put another command in the route section, geom equal to check, then so Gaussian will read this section from the checkpoint file. So same as the one space. Is going to the next section. This is optional section. they have a different, it can use the different type and different purpose. For this section, this example is giving us a connectivity for the molecular connectivity, but most of the case we don't need to use the connectivity for optimization job. So as I said, when you use the mixed basis set, we need to define that mixed basis set in this section. In this section, if you put the different atoms, suppose like this one, and see I want to calculate the silver by using a len L2DZ basis set, and the remaining other atoms I want to calculate by using the 631 G star basis set. That's why just I make a list of the atoms, and this 0 indicate the end of the atom list. You have to put the 0 always end of the atom list, and the next line is what basis set do you want to calculate. And the 4 star, it indicate this end of this type of atom, and you start the second type of atoms, list of atoms, and then last number is 0. Don't confuse with the O, oxygen, and 0, sometimes it's confusing. And second star line is end of this line too. And next important thing is, sometimes it's important, you have to put multiple blank line end of this section, because that means your input file is done. If you don't put the blank line, you will get error messages in the Gaussian file. And you are ready to go to calculations, submit the job. Thank you.
Well, thank Jebet. And questions are very welcome to give him hard time. Or learning something about submitting Gaussian jobs that you haven't seen before.
They are happy. Thank you, guys.
No, you will not go. So suppose you are computing very big system, and your cluster has power outage. You know it for sure. And you want to do part of the job today and second part after Christmas.
Yeah, that's the same, because most of the Gaussian software, they use that what data they already have, they use as a keep that as a checkpoint file. So you can extract that information what you have done so far from the checkpoint file. In the next run, as I said, you don't need to put the Cartesian coordinates system, because you want to the unfinished geometry from the checkpoint file. In that case, you have to put the other route in the command in the route section, the geom equal to check. That means the Gaussian will extract the geometry, last geometry from the checkpoint file. So then they will run for the next calculation.
So you can do 50% of optimization today.
Yeah,
and 50%.
But it doesn't work on all calculation. It's work on the optimization job and with stepwise calculation. Suppose if you're going to TDFT, it don't work. You have to do that because it's a single point job.
Okay, please join me in thanking Jebet. And the next presentation is by Mindika Tilan Nakasinki. So he will share his experience about how to interpret the result Gaussian calculations that have been generated by this code after it has completed. And we are still continuing the game of what would we do if there is no graphical user interface. How to read these plain text files and extract something useful from them. Okay, floor is yours.
Old version, is it okay?
You want? Can you do this one?
We don't have the molecular structure, and it was meant to update it.
Okay. We are still.